So hello everyone. So this finally is the CloudWalk's R&D Symposium. The second edition. We had the first one back in the end of 2021. So just to give a quick overview for you guys, the idea of this symposium comes from our R&D interns. They have like kind of different activities here on CloudWalk. They are developing a research project of their own. So they choose some topics that really not related to CloudWalk activities, and we provide some support for them. So the idea of this symposium is the interns are able to show their work to everyone because they are kind of isolated on their own. So I think it would be a nice opportunity. And also for the first time, we are going to present some works that were developed by CloudWalk full-time employees, including the first scientific paper published by CloudWalk R&D team by Aaryan. So I think that is really good, really interesting. And again, just a quick overview. We're going to have 5 works being presented. Each work will be presented in around, I put here 30 minutes, but you have some works that will be shorter, around 20, some works that will take around more like 30 minutes, so kind of like an average 25 minutes plus 5 for questions. And so we're going to have pre-papers will be available for everyone to read. Pre-papers are work in progress by the interns, but you're also going to have maybe available the PDFs for the works that were accepted in the academic conferences. And the objectives, I think, for the symposium, of course, is to increase knowledge and drive innovation, because greatness cannot be planned. But also, I think, increase awareness of CloudWalk as an interesting place to work, right? Because I kind of don't see many places that doing stuff like that, right? And another thing that we're going to have like some people watching here that maybe are coming from different teams, CloudWalk. So maybe I think could be a good opportunity for you guys to reflect and maybe have some ideas that what could be maybe some future projects for, research projects that we may have, for some pain points or some ideas that you guys may have. I think maybe that could be interesting. You guys maybe could talk with us later. I think maybe, think a bit. So the prospective schedule that we have the first new product development through social media-based analysis by Princesa. And then we have evolutionary feature selection, a novel wrapper feature selection architecture based on evolutionary research, a work by Aaryan Dubey that was accepted in Gecko, a conference in genetic and evolutional computing. So really, really good. We have, after Aaryan, we have reinforcement learning for accurate pointing control of CubeSats in astrophysical research by Bárbara. And then we have FeatGeNN, an evolutionary convolutional model for feature generation by Sammuel. That was an intern back in 2021. And his work, the genetic B algorithm, actually was accepted and became CloudWalk's second paper. And then Sammuel, in this meantime, he became a CloudWalk full-time employee and is presenting yet another work. So, I mean, the guy just doesn't stop, right? And last but not least, we have complex networks and clustering applied to the analysis of the Voynich Manuscript by Guilherme. So enjoy the presentations and sorry for the technical hiccups that we began. So thanks. And I think it's up to with you, Princesa.
All right. Right, so I think you guys can see my screen. So hello everyone, I'm Princesa and I'm one of the AI interns here at CloudWalk. So today I'm going to present about my project, which is called New Product Development, or NPD, through social media-based analysis by comparing word-to-vec and bird word embeddings. So first of all, let us think for a second. What are some of the traditional ways we use to get customer feedback on our product? Well, usually we would answer same things all over again, which is through surveys, focus group discussions, and product trials. However, ways like these have the same problems, and those are that they're too slow, too time-consuming, and too expensive. Just imagine if you have to pay people to review your product, and if you need a lot of people to review your product, then it would be too time-consuming and too slow. So the solution to this is basically social media data. Social media data is free and it's always updated. As we all know, people update statuses, live, and whatever it is, even product reviews on social media data. So my work would mostly focus on retrieving product recommendations for the product development process. So I have mainly 3 project goals. The first one is to compare performance between word embeddings achieved through Word2Vec and BERT. So I will explain to you what those are later. For both sentiment analysis task, so to see whether a certain tweet is positive, neutral, or negative, and opinion detection task, so to see whether a certain tweet has any valuable opinion for product development process. And then the second one is to compare performances between random forest, which is a form of machine learning algorithm, and deep learning in handling small to medium amount of data, which is the size of data that I'm going to use in this project. And the last one is to provide NPD suggestions for the product based on the analysis achieved through the sentiment analysis and the opinion detection tests. So before that, I will explain to you some of the terms that I would be using a lot in this study. So what I'm doing is basically called natural language processing, or NLP. So NLP itself is a branch of AI, artificial intelligence, that focuses on making machines understand natural or human language. So as some of us know, machines cannot really understand raw text data. So what we have to do is basically convert text data into numbers, or factors of real numbers to be exact. And this process of conversion from text to numbers is called the factorization process. And we do this through using a lot of word embedding techniques. But in my study, I would mainly compare between 2 word embedding techniques. One of the most popular, which is Word2Vec and BERT. So Word2Vec is the more traditional word embedding technique. So what differs about Word2Vec is that it's context independent. So it cannot really understand the context of a word. So for example, if you have apple as the input, Word2Vec won't be able to differentiate between apple the fruit and apple the brand. So apple the fruit and apple the brand would have the same factor if you're using Word2Vec. And Word2Vec can understand out of vocabulary words too. Meanwhile, in BERT, this is totally different. BERT, since it's more advanced and more state-of-the-art, it's more context dependent. So in this case, if you have apple as the input, then BERT would totally understand whether what you mean is apple the fruit or apple the brand. So apple the fruit and apple the brand would have different factors in this case. And it also understands out of vocabulary words. And I would also be comparing random forest and deep learning in this study. So random forest is kind of a form of machine learning algorithm. And just like most machine learning algorithms out there, random forest performs as good with small to medium amount of data. And compared to deep learning is more advanced, and it can handle many tasks at once. What we call it is by multitasking. So with machine learning, you have to make each model for each task. However, with deep learning, you can make, for example, like one model to do 2 or 3 tasks at once. But deep learning is also thought to perform worse with small to medium amount of data, which then comes to the next point. So deep learning needs more computational resources, it needs more time, and just like what I've explained to you before, it needs more data. So it needs a lot more resources than classic machine learning algorithms in general. So let's get into the experiment. So the product that I'm going to be using in my study is airline services, as you can see here. So I would be using 6 US airline services. I look into 14,640 English tweets about 6 US airline services. And as you can see here, the data set is pretty imbalanced, with negative tweets having the most tweets, and then followed by neutral and positive tweets. And then I labeled manually around 300 tweets for the opinion detection task. So when you can see here, these are some samples of the tweets. You can pay attention to 2 of the tweets here, which is both negative, both have negative sentiments. However, one is labeled as no, it doesn't have any valuable opinion for product development, but one is labeled as yes, it does have valuable opinion for product development. The difference in this is that in this tweet, in the first negative tweet, you don't have any visible reason on why it's negative. See here, it was a disappointing experience, which will be shared with every business traveler I meet. However, the author didn't say why it's disappointing. So the opinion must be no. So we don't really know why it's disappointing, right? Why it's negative. However, in the second negative tweet, you can see here that you guys messed up my seating. I reserved seating with my friends and you guys gave my seat away. I want free internet. Basically, the reason why the tweet is negative is that one, the author is mad at the airline service because they messed up his or her seating. And second is that the author wants free internet. So yes, you have a valuable opinion for product development. And that's why the label is yes here in the opinion class. So I practically apply all this to the other 300 tweets. And so let's just get into the results. So first of all, the results for random forest. Here I'm comparing mostly between Word2Vec and BERT, which are the 2 word embedding techniques I explained earlier. And as you can see here, BERT performs better in both tasks. In sentiment analysis, BERT performs better, and in opinion detection, where you detect whether there is valuable opinion or not in a tweet, BERT also performs better. So since BERT performs better than Word2Vec in both cases, I took BERT and test it with deep learning. Right, and here I'm mostly comparing single task to multitask. So single task is mostly, so I make one model for sentiment analysis and one separate model for opinion detection. Meanwhile, for multitask, I make one model to do sentiment analysis and opinion detection at the same time. So as you can see here, multitask performs a lot better than, well, not a lot better, but perform better than single task models. But you can see here for the multitask model, for the F1 score, for the opinion detection, that it's pretty low. So we can actually kind of say that the model here cannot really handle imbalanced data, since the data set is pretty imbalanced. So we should compare that again with the random forest one previously. So this is the model's ranking overall. For sentiment analysis, multitask with BERT using deep learning performs best. Meanwhile, for opinion detection, single task BERT with random forest performs best. So now the question is, which model should we choose? I'm choosing single task BERT with random forest because, as you can see here, as I explained previously, the models with deep learning perform bad in the opinion detection task. And meanwhile, for the single task models with random forest, it performs not as good as the deep learning models in sentiment analysis, but it's pretty acceptable. But in the opinion detection, for the deep learning models, it performed pretty poorly. And then the second thing why I'm choosing random forest models with BERT, it's because the goal of my study is to find the cheapest and the fastest way to retrieve opinions from social media about product development, right? So if we're just going to use deep learning, then we would need a lot more time, and then we would also need a lot more data, which is not the goal of my study here, and why would we even use deep learning when it's performing poorly, right, in the opinion detection? So that's why I'm choosing the single task BERT with random forest in this case. So after achieving this, I'm basically making clusters to see the best recommendations for the product. So how I do that is basically I separate the tweets into two, positive and neutral in one group and the negative in one group. And then I construct a co-occurrence matrix using TF-IDF to retrieve the most important words, so that there are 4 clusters for the results showing recommendations for product development. And this is from most important to least important. So the most important thing for customers is time efficiency. So early arrivals, delayed flights, canceled flights for all the airlines is the most important for customers. So my recommendation is that airline services should focus the most in time efficiency and avoid delays and canceled flights. And then the second most important thing for customers is flight or booking problems. So basically, make booking as easy as possible for the customers. And the third thing is facilities, things like seats and then Wi-Fi, movies during long flights. And the last one is customer service. I'm going to show you the visualizations for the most important words so that it's pretty explanatory. So the first one, this is for time efficiency. Here on the left, you can see the most important words in the positive and neutral tweets. You have early here, which shows that early arrivals is pretty much a positive thing for the customers. Meanwhile, for the negative, you can see here late, and then delayed, cancel, miss, and things like that. So time efficiency is the most important thing for airline services in this case, and airline services should really avoid delaying or canceling flights. And then the second one is flight and booking problems. Here, I'm mostly looking at the negative group. Here you see reservation, change, and online, and wait, and things like that. So basically, make booking as easy as possible for the customers, and make sure that it's not too slow or you have to wait really a long time to just book a ticket. The third cluster, which is the third most important, is basically facilities. Here in the positive, you have a lot of things like seat and then flying experience and stuff, and you even have routes. Here you have Dallas and Austin, which is the name of this of cities in the US, which says that routes that are unique are also important for the customers. And here in the negative, you have seat and things like that also. And then the last one, surprisingly, the last one is in customer service. So this is pretty explanatory, self-explanatory if you see the words. So for positive, you have customer service that is very helpful. It would make a great experience for the customer. Meanwhile, for the negative one, customer service that is not helpful is definitely not something that the customer would like. So the conclusion to my study is that 1, BERT is generally better in this case, and that single task machine learning with BERT is the best choice for both sentiment analysis and opinion detection, considering the cost, which is mostly time and the amount of data needed. And then the third one is that recommendations for the product. First, time efficiency is the most important. So airline services should focus the most on time efficiency. And then there's flight or booking problems, facilities, and customer service goes last. All right, that's all for me. Thank you.
Thanks, Princesa. So, does anyone have any questions for Princesa? Well, I guess not.
Yeah, I do
But
only have one
oh,
comment. I do have only one comment that it's not a question. I think it would be interesting to compare this. I know it's kind of hard to do and maybe a little bit boring, but compared to a human, like you should do like a a control group test, like get a human, give him like some, I don't know, 1,000 tweets. The human classify the problems, and then we see if the distribution, like if he finds that the reach the same product suggestion, like, oh, if you have the kind of the same, find the same topics, like where we should improve. Because I think this is extremely valuable. Like, is my intuition as a human looking at some tweets the same as BERT model? That would be my suggestion for maybe a future comparison.
That sounds interesting. Yeah, really nice. So yeah, if you guys want, you can always ask Princesa on Slack. So congratulations, Princesa, on your presentation. I think we can go to the next one then. So Aaryan, can you present?
Yeah, I'm going to just share my screen.
Good.
Tab. What is feature selection? Can you people see my screen right now? I don't know.
Let's wait a bit.
Okay.
Yes, good to go.
Okay. Hello, good morning, everyone. My name is Aaryan Dubey, and I'm going to present on evolutionary feature selection, a novel wrapper feature selection algorithm based on evolutionary strategies. So, what is EFS? EFS is a novel feature selection algorithm that selects the best set of features for a machine learning model. It uses meta-heuristic techniques combined with evolutionary algorithm and chaos theory. And also, it uses the concept of evolution, which is the backbone of our algorithm. So, what is feature selection? And it's important. Feature selection is an approach to selecting the best set of features from a feature pool. The goal is to increase the performance of the machine learning model. So, now let's dive into some feature selection steps. So, first step is subset generation. So, in this step, the algorithm tries to generate a subset of features out of a feature set. Let's just say we have a set of features A, B, C, D, E, and F. We generate the subset of features like this: A, B, T, F, A, B, E, F, and A, B. So this is how we generate a subset of features. And after that, we use this subset of features like A, B, D, F in a particular machine learning model and get a score like, okay, 0.85 is the F1 score. So this is how we evaluate this subset. Okay, the subset is performing well. And this process of subset generation and evaluation goes on until a termination criteria is reached. After that, we take the best set of features and evaluate it on our test data set. So this is the feature selection step. Subset evaluation in Python, the step which I told you earlier, we take the subset of feature A, B, E, F, we put it into a function and get an integer value. Here, this is a particular class which uses a function that is FeatGeNN right now. It returns a particular score if we initialize certain features here. Encoding. So what is encoding? It is the process through which we represent our data to a particular format. Famous example for this could be where we convert the decimal number to binary number, like number 6 is converted to value 0, 1, 1, 0. So what is this encoding and how do we use this encoding to encode features? Let's see. First, we need to understand the concept of generation, chromosome, genes, active genes, and non-active genes. First, chromosome. Chromosome is an array where you can store data set right now, like 0, 0, 1, 0, 0. It's our data point that you store in an array. So right now, chromosomes represent that array. Genes represent those data points, that is 0, 0, 1, 0, 0. These data points are known as genes. And inside that data point, the active genes are represented by number 1 and non-active genes are represented by number 0. And if we combine this all data, we put it into a particular set, it is known as a generation in context of EFS. So now let's just see how we encode these features. First, we have a particular set of features. A, B, C, D, E, F, all these features are selected. So we use all the active genes to represent it. A is represented by active gene 1, B, active gene 1. Similarly for C, D, E, F. Now, if we try to encode A, B, D, and F, here A, B is represented by active genes. That is 1 because they are selected. D and F are represented by active gene again because they are selected. Similarly, C and E are represented by non-active genes, that is 0. So this is how we encode our features in the evolutionary feature selection. So what is this EFS architecture that we talk about? First, we need to understand the EFS generation. Generation, in simple words, all the people born and living at about the same time. In EFS, the generation is the number of times the new subset will be generated in the single run of the algorithm. So that means if EFS run for 10 generation, for every run, there will be a subset of features generated encoded in our encoding. So we call this architecture evolutionary strategies. The basic idea for evolutionary strategies is the number of active genes in a chromosome is increased by each generation. So suppose that we have 10 features in our feature set, like feature A, B, C, D, E, F, G, H, I, and J. So in first generation, we can obtain a possible chromosome of value 1 active genes and 9 non-active genes. Similarly, for second generation, we can obtain a chromosome value of 2 active genes and 8 non-active genes. This process grows with the number of generations, as mentioned earlier, so that the earlier generations have fewer genes as compared to the advanced generation. Through this strategy, we can have a set of features that have been truly evaluated over the generation. This particular idea of evolutionary strategies is inspired by the NEAT algorithm, that is the neuroevolution of augmented topologies. Here they evolve the particular neural networks, that is the structure of the neural networks. So we take this idea from there and some concept of evolution to evolve our architecture here. So evolutionary strategies. The basic idea is number of active genes in a chromosome is increased by each generation. So in generation 1, we have chromosome with encoding something like this with only 1 active gene. In generation 2, we'll have chromosome with 2 active genes. In generation 3, we will have chromosome with 3 active genes. So as you can see, the number of chromosomes are number of active genes in chromosome is increasing by each generation. So what happens in each generation of the EFS? So let's see. First, we create a new random chromosome. We put it into the local list. We evaluate these chromosomes. We terminate some of the chromosomes here that is not useful for us right now. We create the best set of chromosomes. After that, we put the best set of chromosomes into the global list. The global list, it goes to the crossover and the mutation operation. After that, we have a new set of chromosomes generated. New set of chromosome generation will go to the evaluation step again. Again, the termination step will happen. It will again add to the global list. Now, let's understand the random chromosome initialization. So, random chromosome initialization. In general words, this step can be known as the subset generation step. So, in generation 1, we will create a subset of features like this, where we have only 1 active gene. In generation 2, we'll have subset of feature with 2 active genes. In Python, we represent this particular chromosome with this type of code. So, now let's just see chaotic random chromosomes generation. First, we need to understand some variables. What is pop size is the number of chromosomes in a generation, that is 1. Temp size is the number of active genes in a chromosome. Right now, we are using only 4. Number of column, that is the number of feature set, that is right now we are using 10. So we create a particular loop. We use equation 3 that is written here to calculate init lambda. We take this init lambda, put it into equation 4 in place of lambda list n-1. And we need a value for every active gene that we have. So right now we have 4 active genes. So we'll calculate this value for every active gene. So at the end, we'll have an output of something like this, a particular value for every active gene that we have, that is 4. After that, we are going to use this lambda list value that is here and put it into equation 5. Now we are putting this lambda list value that we have in equation 5 and calculate the value r. We already know what is the value of r, that is 2 into lambda list, n is to number of active gene minus 0.5. We calculated temp list is the index of our features 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now for every active gene, we use the r value in equation 5 and calculate our sample, that is an array which will store all the indexes. At the end, the final output will be something like this: 4, 6, 5, 8. That is the number of the active genes indexes. So if we translate it to chromosome, we'll have something like this: 0, 0, 0, 1. That is the 4th index is selected here. 5th, 6th, 7th is 0. Now 8th index, 8 is 1. So this is how we generate the chaotic random population for our EFS. So mutation. We use two mutation operation. One is simple mutation operation. Here we take a chromosome 1. We select a particular index. In this case, let's just say index that we selected is 2, right? 0, 1, 2. We just flip the bit. That is 0 is converted to 1. So we get our mutated chromosome. So this is known as the simple mutation operation. Now we go to the chaotic mutation operation. We select a particular chromosome, chromosome 1. We take a particular mask and we perform the OR operation between them. That is 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. So this is how we perform the chaotic mutation operation. After that, we go to the crossover operation. In crossover operation, we use 3 operations. That is the simple crossover operation. Here we take 2 chromosomes, chromosome 1, chromosome 2. We divide those into half. The first half of the chromosome 1 will be inputted here. The second half of the chromosome 2 will be inputted here. And we have our new chromosome. Now, we go to the random crossover operation. Here, we take 2 chromosomes, chromosome 1, chromosome 2. We select a particular random index. Let's just say index is 4. So 0, 1, 2, 3, 4. We draw a line. We take the first half of the chromosome 1, we put it here. We take the second half of the chromosome 2, we put it here. So by this value, we have a new chromosome value. That is 1, 0, 0, 1, 1. After that, we have a uniform crossover. In uniform crossover, we have 2 chromosomes, chromosome 1, chromosome 2, and a particular mask that is initiated from chromosome 1. Now, what the mask value will do is, we take the particular value that is 1. So, if the mask value is 1, it will take the value from chromosome 2. If the mask value is 0, it will take the value from chromosome 1. So, this is how we create a new chromosome in uniform crossover. After that, the main thing. Initially, the mask is generated in random chromosome initialization phase. But things differ in case of crossover operation. Let's believe that we have a particular chromosome A and a chromosome B. We perform a crossover operation between them and create a new chromosome, that is chromosome AB. So, what mask will the new child chromosome will contain? And how do we create this mask? Let's see it. First, we need to use these steps that we have written here. First is convert the mask from gray code to binary code. We already have our mask value from chromosome 1, that is 11001. We convert the mask value from gray code to binary code using step 1. We get the binary mask value, that is 1001. And we initialize the step 2, that is convert the binary mask to decimal using equation 8. We use the equation 8, convert it again. We get the 9, that is the decimal value mask. Now, we are going to use the step 3, that is convert the decimal mask value to real representation using equation 9. We go to the equation 9. We see that K is the number of bits used for binary representation, UL is the upper bound, LL is the lower bound. We use it as 0, we use it as 1. Mask and decimal value we already have, that is 9. LL is the lower bound, we already know it. If you put these values in equation 9, we'll have something like this: 0 plus 9 into 0 minus 1 divided by 2 is to power 4 minus 1. We'll get a real number mass, that is 0.6. After that, we apply the step 4. What is step 4? Step 4 is calculate a new mask value using equation 1. Here, equation 1 is chaotic logistic map equation, where xn is defined by xn, that is the value between 0 and 1. And here, if the theta value is between 3.57 and 4, the logistic map equation is proven to be in a chaotic behavior, excluding some periodic windows. Here, we already know the value of xn, that is 0.6. Theta value is calculated same as we have calculated this value of 0.6. Similarly, as we have written here, similarly for theta mass value 0110, we'll have the value as 1.066. Same as the step we have calculated 0.6. Now, if you put these both values in step 4, now we have the theta value, we have the xn value, and we put in the step 4, that is calculate a new mask value using equation 1. we'll get the value as 0.256. After that, we put the step 5, that is convert the new mass value to decimal value. We get the 3 as the new decimal mass. We use the step 3, that is convert the decimal mass to binary. We convert it, we get 011. We use the step 7, that is convert the mass from binary code to gray code and store it. We have this value 0010, that is the new mass for the chromosome. Some miscellaneous term. What is the local list? Local list is an array which stores the random chromosomes and track them and evaluate them. Evolution step is here we terminate the features that we have created so that it can only pass through the best chromosomes that we have. Global list is the global array which stores all the Voynich chromosomes through the generation. I'm going to pause here and ask, like, does anyone has any questions right now? No. Okay. So after that, we know that these are the things. So simple flow of the diagram, what we have learned right now. We know that what happens in each generation of the EFS. So we run it for 4 generations, right? For every generations, we perform the crossover operation, we perform the mutation operation, we perform the evaluation things, and we update the global list accordingly. And in the whole generation process, global list will have some certain values that will be terminated from it, certain values that will be added through it. The evolution of the creatures will happen in this particular simple flow. And after that, generation 4, we'll just print out the global list and it will have the best set of features. That's it. That's the EFS. We already defined what is chaotic chromosome initialization, how we evaluate creatures, how we select the chromosomes, the global list population, the crossover and mutation operation. That's it. That's the EFS. So some memory refresher. So we already know we have chromosome A, chromosome B, the code counterparts of how chromosome A and chromosome B are created. So let's just say we create a child chromosome, chromosome AB from chromosome A and chromosome B. Right now you can see we have 2 parents, parent 1 and parent 2. Parent 1 value is 25, that is has come from chromosome A, that is the number 25. Chromosome B has the value number 15, it will be used here. So chromosome AB has been crossover from parent A and parent B, that is 25 and 15, chromosome A and chromosome B. This will be useful for us to understand this, the evolution cycle of the EFS. So let's just say we run the EFS for 4 generations, and the best generation was generation 4, where we got our creature 737. In the 4th generation, the value in the parentheses represent the generation in which the particular creature or chromosome was created. So as you can see, the answer that we have here, that is the 737th creature, was created through the crossover operation, as there are 2 arrows to the particular node from generation 3. And in generation 3 creatures, that is the 597, which was generated in generation 3 through the mutation operation from generation 0. That means generation 0 mutated to form the creature in the generation 3, which in case performed the crossover operation with another creature from generation 3 to create our answer. This is a simple flow of how the evolution cycle in the EFS happened. Let's look at the more complex flow of the diagram. That is this. As you can see, we double the number of generations. Right now, we have 8 generations here. And the generation that is a 0 generation influence in the last generation has increased a lot. Here we have only 3. Now we have 6. So as you can see, the 8th generation was created from 5th generation and 7th generation crossover. That means 5th generation creature has survived the ordeal of 6th generation, 7th generation, and has come to the 8th generation to form our best creature. That is the 1581th creature that was generated in 8th generation through the crossover operation between the 7th generation and the 5th generation. And also, it doesn't qualify like if you're working like very hard that you are going to survive through the environment. As you can see, this 4th generation creature didn't make it to the end. That it has any help in creating this generation 8th creature. So it died at the generation 4. So these type of things also happens in the EFS. In the more complex diagram, we will see some creatures value that will be created in generation 4. That means it didn't evolve through any generation. It was randomly created in generation 4 and can help us to reach our best creature. So this is just a simple and some complex cycle of the EFS. So some data set and parameters that we use to test our algorithm. So We used the 10 data sets. Out of the 10 data set, 3 were the multi-class data set and other were the binary data set. The parameters that we used were the number of generations were number of features -1, the number of runs that we did were 10, the number of creatures that we created were 200. Experiments. So first experiment that we performed was using the matrix, that is the CubeSats classifier. The evolution method that we used was the accuracy score. So in table 3, you can see the comparison between the EFS and the other methods that uses the same classifier. That means the CubeSats classifier. So out of 9 data set, EFS outperformed the other algorithms on 8 data set. And out of 8 data set, we were on par with QBSO-FS, that is in Zoo data set, and in Congress data set, we were on par with the QBSO feature selection algorithm. We were outperformed on Sonar data set by CSSA algorithm. After that, we performed another experiment, that is experiment 2. In experiment 2, we used the 3 matrices, that is SVM, naive Bayes, and AdaBoost. We used 2 data sets. In first table, you can see the data set is known as the spam-based data set. And in the second table, we have the data set known as the Sonar data set. The numbers in the parentheses represent the standard deviation of this whole algorithm of our runtime in the 10 runs. As you can see, in the first table, we were the best performing algorithm in naive Bayes and AdaBoost classifier, but we were outperformed in SVM by PSO algorithm. Other than that, on the Sonar dataset, we were the best performing algorithm out there. As you can see, the standard deviation of our algorithm is lowest in any of the particular algorithm that exists there. So this proves that our algorithm is one of the best feature selection algorithm out there with the most consistent results. So the main question, why does it work? So in the algorithm, the number of generation, that is the number of features, is directly proportional to the number of generations, which gives it a larger search space for a given set of features. This property allows EFS to grow slowly and effectively with the increasing generation, which leads to a better solution approach in most cases. In addition, this property can make the algorithm a time-consuming process for a dataset with a large number of features and samples. So yeah, that's it. And at the end, I just want to thank all the authors, that is Sammuel Silva, Pedro Teja, and Alexander Ino, for all the help and support in making this paper successful. Thank you so much, everyone. And yeah, that was me. Thank you so much, everyone. This was presented by me, Aaryan Dubey. You can find the evolutionary feature selection on the GitHub through this link, or just go to the CloudWalk GitHub. It's open source right now. Thank you so much, everyone.
Thanks, Aaryan. Really nice presentation. Really nice that you put GitHub, so it's like open source, CloudWalk open source, right? Initiative. So, guys, does anyone have any questions for Aaryan?
No
Kind of
questions, just another comment. Just so everybody knows, we use this in production here at CloudWalk. So this is what we use to improve our models, and it's really effective, especially for detecting frauds on card loan presence. Yep.
I have a question actually for Aaryan. Like, when did you start working with EFS here? Because I remember it was something that when you entered CloudWalk, you started working, right? So
yeah, the day I entered CloudWalk, I started on this project only, and it evolved through this. This is the final project, final form of the project, I would say. But yeah, still there is evolution thing that we can add on to it. But yeah, the day I entered CloudWalk, I was introduced the NEAT paper, and then we had this idea, and we worked on it. So,
yeah, you see. And when you entered CloudWalk?
This, I think, December of 2020. 2020, yeah, December 2020.
Oh, you see? So yeah, really, really good. Really interesting, Aaryan. Congrats.
Thank you so much.
May I have a question too?
Yeah. Please.
So it's, first of all, congrats. That's
Thank
very
you.
cool. And what I think is that it's very interesting, we taking kind of inspiration on how nature works to create a more intelligent exploration of this feature selection space. Do you see any other for example, you talked about many of the ways that we are combining the genes and mutating them. Do you see any complexity that could still be added to the EFS or to a following model that follows this genetic evolutionary theory, like that was harder to encode, that we were not able to create a different way of visualizing it or to applying it?
Generally, I would say like we depend a lot on, like in CloudWalk problems, I would say we depend a lot on random solution approach. Like any random solution will be created in generation 4, and then we can have an answer in generation 8, something like that. So random chromosome creation plays a very important role. But in other academic, if you go and see the academic papers, they don't depend much on this random initialization. They try to go like from first generation of creatures. So that is something I would love to see, like how a generation creature that was created in generation 1, can evolve to generation 8, something like that. That is one of the thing. And other than that, I believe there are tons of things that we can incorporate into this particular algorithm. We still don't know it yet, I would say, but inspiration is all around us, I would say. So every day you see something and see like, okay, how can we implement it? So yeah, that's the thing.
Okay, I will add something to Joel's question here. Not another question, like comment, like, well, because here we're encoding one feature as one complete gene, and this is not actually what happens in nature. We don't have a pool of genes, like you have you have NDA. There's a 4 bases of per acids. I'm not too sure. Then the combination of these elements, then you create in a sequence. Then you find a gene or create a gene from there is no pool of genes where we active or deactivate. There is only the creation of genes based on raw data. This is extremely hard to do. Automatic feature creation. This to be able to do this would be a huge milestone. Yeah, and also encoding other stuff, because we are only encoding features here, but the next step is to encode hyperparameters. And this is also hard because hyperparameters are not like discrete, like are active or non-active. They have a value from 0 to 150. How we encode this in a way that is similar to a genetic algorithm, it's not obvious. Also encoding the topology of the model. Like here, Aaryan is using the same architecture for all creatures. Like they're running the same architecture. They're not evolving the shapes of their bodies, what would be the architecture. So there are plenty of stuff to make it more complex, but it's really hard to figure out a good enough way to encode data. Yeah, I would say that.
Very cool. Thanks, guys, and that's very interesting. Congrats.
Thank you. Stop.
Yes, I think now we can go to the next presentation. Bárbara?
Okay, I'm presenting my screen.
Okay.
All right. So hello, everyone. I'm Bárbara. I'm an intern here as well. And my project is about reinforcement learning for achieving accurate pointing control in CubeSats that are used specifically for astrophysical research. So when we think about astrophysical research done in space, it has some benefits, like not having interference from Earth's atmosphere and other stuff. But we mostly have examples of satellites or telescopes that are not exactly satellites. For example, we have James Webb here, which is pretty famous, not exactly orbiting the Earth. And then TESS on the left, which is a telescope and also a satellite that is was very good in detecting exoplanets. But what they still have in common, despite of just being great, and what they do is that they take long time to develop, like decades, and they are also very expensive, and they are not built to be exactly specific to, for example, a specific cluster of stars or a region of the sky. So if you want to develop something more specific, more cheap and fast to build, that won't last that much, what do? So one of the solutions for that is CubeSats. So CubeSats are a type of satellites, and they have this name because they are in the shape of a cube. They have standard components, and they have standard way to build. This is why they're so cheap to build and to develop and to launch. And they can be used in many different fields, and they're used in astrophysics. It's still being explored, but they do have the benefits of the price, and also they can be more specific if you want to observe specific stars, for example. So depending on what kind of research you're going to make, of course, you can make all types using CubeSats. But talking specifically about photometry research, which is observing the brightness of stars, you can do that for analyzing, for example, detecting exoplanets. They have some problems that you have to account when developing that, so they can still be useful and precise. So because they're small, the system we use to control its position, its axis, can affect the data and observations you're making. So usually you use in the ADCS, which is the attitude determination and control system, usually you use magnetotorques or reaction wheels, and these components, they are precise, but if you're using in a CubeSat, which is small, and also for that kind of research like photometry that requires high accuracy and steady control of the satellite, this can cause jiggles. So you're trying to point to a specific star, and then the CubeSat will have some jiggle, and the data won't be exactly precise. So you have to account for that when developing that. One of the methods that is the most effective was done by Aaryan, which was the first CubeSat in astrophysics, and is using a two-stage approach to doing that. So on the image, you can see the second stage of the correction, and talking more about it. So the first stage will be the normal stage of pointing control, so the reaction wheels and the ADCS, as I said. So it takes the first action to the star. And because of the natural imbalances that occur in this kind of component, and because CubeSats are more sensitive to it, the target, will have a little bit of a difference between where you want it to be and the sensor and what it is. And then they use a second stage, which is right behind the sensor, using just to focus the sensor itself and make the corrections from the deviations that were made on the first stage. So this method is very, very precise. It's one of the best we have. Here you can see the motion of the star on the photometric sensor, considering the first and the second stage. So in the first stage, you see that it is precise. It's a good technology, considering you have like a range of around 4 pixels, but it's not good enough for photometry. So using the second stage, it is very steady on the sensor, and it also has an accuracy that's less than a pixel, so considering an arc second of the CubeSat. So in my project, what I want to do is to test different ways of doing this second stage correction of jiggle correction of CubeSats used for photometry measurements. So considering just the second stage, correcting the deviations from the first stage. So what I will do first, I have to develop an environment to use reinforcement learning in that. And in this environment, have to consider what kind of parameters you're going to put in it to have an accurate simulation of it. And also explore if reinforcement learning, which is a type of machine learning, is feasible on this problem, and maybe could have some benefits, like reducing the time you have to process and calculate the corrections. So reinforcement learning, as I said, is a type of AI, and it's a little bit different than the others because it's about how an agent interacts with its environment. So the environment has states, and the agent will observe that and then choose an action. And then that action will cause something in the environment, and then you'll tell the agent this is good or this is not. And then it will learn by reinforcing that behavior. So its main goal is to get the most reward it can. So in the end, it will learn the behavior you want it to do based on the reward you give it. So you can do that in different ways. There are many ways you can train an agent to learn a certain behavior. So there are many algorithms for that. In my research, I used mostly TD3 because it was the most effective for this problem. So TD3 is what came after DDPG. DDPG was already an algorithm that had good results in its applications, but TD3 improved some of its problems. And it has so many little details and layers of how it works that it's really hard to cover all of it. But basically, what it has different from the DDPG is that it learns two key functions and it has two critic networks. And it also has a delay update to the agent about the critic network. Also add a little bit noise for the target action. And it also is a type of algorithm such as the DPG that has two different types of network, so the actor and the critic. But in this algorithm specifically, it has two critic networks, so it added a little bit more of evaluation to correct the problems that the DPG had before. So here you can see a little bit how the feedback from the environment gives information to each of the networks. So the actor network is the one that will get the observations of the agent and then output an action. And the critic network will get the action and will say, and will evaluate that. So say, well, this is good, this is not. In the case of TD3, it has two critic networks, but it's basically how this works. So other than that, TD3 also works with neural networks and all. But this specific detail of the actor and the critic networks is what is most important to understand about it. In order to train the environment with this algorithm, we have to be very careful with what we consider in this environment. So considering it is a very specific problem, we have to think, what will we put in this environment to train an agent specifically for this problem? What parameters do we consider? So this environment has very specific details, and I'll cover them right now. So the agent that we will consider will be the piezoelectric stage. So this is the component of a satellite that was used in Asteria that was responsible for making the corrections from the first stage. So it accounts for the deviation in the first stage, and then it moves to make the corrections. The animation you can see on the right is an example of piezoelectric stage. So it is a very precise type of stage, and it is to the nanometer precision. It is a nanopositioner. So the way we consider the action, we consider the voltage because the displacement will be proportional to the voltage applied by the component. And then this displacement has a range. It is a continuous action space, so that means it has a range, not a specific set of actions you can take. But the range goes from what it has left to move through the whole environment. So it can move through the whole environment, and each action it can take depends on its position in the environment. But basically, it works just like you see in the animation. It can move through the whole environment with a range of actions. This environment, the agent always in the middle to focus the stars. So what is moving is its whole view. And then you see in the animations, it is always fixed in the middle. Also, we have the stars. So instead of just having the target star and then telling the agent where it is, we have a constellation of stars, and then it has to find where is the target star based on a predefined shape it has to find. So in the example, we have a constellation, and then the star that has a little bit of different shape, you can consider as a target star. And then the environment and the agent will have to find the target star based on a predefined shape that has to match, and then it will get that information as a target star based on its position according to the other stars. These stars also are not just, for example, a pixel. They are a blob, so a variation of brightness, and they have different layers of brightness. We'll talk more about this on the next slide. The reward that is given is proportional to how distant the agent is from the target star. So the more close it is to it, greater will be the reward, and it is perfectly aligned with it and maintains it, the reward is the greatest. And then, as I said, this environment is just to simulate and learn the corrections from the first stage. So it's just the second stage, but the first stage here is represented by the difference in the spawn points between the target star and the agent. So it will be the deviations from the first stage. And this value is not like completely random. It is generated based on the values from the first stage. So it is all proportional. Also, this environment also has all the values in accordance with what will be in real life. So you can get all the results and also in actually compare it to what we get in real experiments. So about the centroiding, as I said, the star is a layer of brightness, not just a specific point in it. And the first image we have on the top is an example. We have 4 different layers of brightness that are generated by the environment, and then there is a different algorithm in the environment itself that will find the centroid. The centroid will be the center of the star, like the brightest part of it. This centroiding algorithm, it is the GF, Gaussian fitting algorithm. It works by considering that the distribution of brightness in a star follows a Gaussian distribution. It's also called a normal distribution. This is a type of probability distribution in which it has many details on it, but basically you have the mean, the mode, and then the median are all on the same point, and it has this bell-shaped curve. But what it is important to notice here is that there is an algorithm that runs in the environment to find the centroid. It also has some adaptations to account for a problem that is normal to occur, which is the temporarily bright pixels. On the image, you can see are the white dots that are on the background. This happens normally, and the algorithm accounts for this by not just taking the brightest pixel as the centroid, but it has to have a match with a range of brightness around it. So it won't just take blindly the brightest point and consider. That will be a problem. And then, as you can see, it works perfectly. On the second image, you get the red dot right in the middle, which is where it's supposed to be. So it works to find the centroid, and also it's not, it doesn't have a problem with the temporarily bright pixels. So now how to understand it better, how this works in the whole environment. Here we have the 2 stages. This environment considers just the second stage, but the first stage is just a value, a specific number. And this number generated proportional to what it would actually be. So here I considered all values from the stereo CubeSat, so all the inertia values to have the proportional force to be applied. Then we have the angle that is randomly generated that will generate a torque that will be applied by the reaction wheel. This value will generate a proportional distance between the star and the agent, and that will be what the agent has to correct. So then the environment generates the stars. As I said, it is layers of brightness. Since it has to first point and then maintain it, it also has a constant speed. So the stars are moving with a constant speed and the agent has to maintain it. And then we have the algorithm that gives the input, the output as the centroid. And then what is in gray in this example, it's what the agent has an observation. So all of these values, what the agent has as information about the environment, and it will learn according to it. So this is the environment before training. So as I said, it does have layers, but here you just see a dot, which are the stars. This is because rendering the environment, considering all the layers of brightness, it was very heavy, so it wasn't really possible. So what you see here, the dots are actually the centroids. But keep in mind that we do have the layers of brightness. The pink one in the center is obviously the agent, and then the red stars, the red star is the target star, and the blue stars that you can see in the start are the guide stars. And this is the environment before you train. As you can see, there is a constant speed that the stars move. And then before training, the agent is taking random action, so it doesn't align with anything. And then we train it. As I said before, we use mostly TD3 because it was the one that has the most effective results. But this graph, you can see how the centroid information was very important to achieve high accuracy and also a high learning rate. So on the y-axis, we have the success rate, which is the amount of time, the percentage of time during the episode in which the agent is aligned with the star, with the target star. And then on the x-axis, we have the episodes. So before we have the central information, TD3 was still the best one, but it didn't have a clear learning curve, so it didn't exactly got a stable point after all those episodes. And also it didn't achieve more than 95% accuracy. But when I put the centroid information, so all the brightness layers and the centroid information, the learning curve got way better for both TD3 and the DPG. The accuracy, so the success rate of the environment became 98%, which is very, very good. And also there's a clear learning curve, and TD3 does get stable after training. So when it does get stable on the second graph, you can see that's when it got trained. So 98% of accuracy, it's probably the highest we could achieve, considering that they are spawned in a different position. So it does maintain for 98% of the time. So that is pretty much most of the episode, considering it is spawned differently. And here you can see the training. So as you can see, the agent is 4 times bigger than the target star. This is because what is actually a pixel, like in proportional here, is the pink dot, so the agent. So as you can see, the precision here is less than a pixel, so a fourth of a pixel, which in a stereo would be basically an arc second. So this precision is to the arc second level. And as you can see, after training, it does maintain. It's not moving anymore because it is maintaining it during the observation with the constant speed. It does have some deviations that I added to the environment just to simulate the normal deviations that would happen. But even with that, it was able to maintain in the pixel of the agent. So it is a very good result. So in the future, what I do still want to test is model better the first stage. So right now it's just a value, but we can also consider the 2 stages together, not just a value from the first one. Also test different observation. As you saw, centroid information was very important for the learning of the agent. It's a very important information about this type of environment. So test different things and also test different ways of giving the reward to the agent and different cost functions. And yeah, that's it, guys. Also, I want to give special thanks to João and Fabio from the R&D team. They also helped me a lot in this project. But that's it. Thank you for your attention. And yeah.
Nice, Bárbara. Congrats. Oh, and congrats also Fabio as well, right? So guys, do you guys have any questions for Bárbara? Well, I actually have a question for Bárbara. My question is how it was, because mostly for reinforcement learning, like when guys show work is like video games, so like how the agent plays video game and stuff like that, and that's the environment, right, that you created. So I don't know how it was to create the environment, and what do you think we were able to model, and what do you think you can improve on your environment?
Yeah, so the environment is really the hardest part because I didn't have much examples to base myself on, and it's also a very specific problem. And since I'm starting on like machine learning and also on the engineering part, it was a challenge, but it was also I learned a lot about reinforcement learning just by modeling the environment. There are a lot of things we can still test and add. I think the centroiding part was very interesting, how it actually improved the learning of the agent. So it is very curious how there are many things you can consider to actually make this very feasible in real life. So I think that the next step would be to better model the first environment, so we have a better correspondence from the first stage deviations to the second. This is also a very hard thing to do, but I'll definitely go for it.
Yeah. I think, the centroid, right, this information of maybe the agent knows he's getting closer, I guess, maybe.
Yeah.
Really, really interesting. Any more questions for Bárbara? Okay, then I think we can go to the next presentation then. So thanks, Bárbara and Samuel.
Okay,
Good.
just wait here. Okay.
Yeah, good to go.
Okay, guys. So I'll be presenting another work that I'm currently doing, other research that I'm currently doing. That is focused on creation of features. So it's called FeatGeNN, an evolutionary convolutional model for feature generation. I forgot to turn off my webcam, but well, I already started. So the problem.
You can turn on now, don't worry.
Okay. Uh, sorry about that, guys. I'm not used to. Okay, you guys see me? Hi. Just a little bit better. Okay. Uh, so yeah. So what's the problem, right? We want to create new features. So give a set of features that we have as a data set, for instance. We want to improve the evaluation metric. So one way to do that is we can decrease the amount of features, right? Is the method that Aaryan used in the EFS. And another way to do that is to add new information. So we can add new features, and add a new feature, we can may result in a more accurate model. Because if you add a lot of features, also you can the model can at the, cannot learn so well also. So we can have to keep the balance between the amount of features that we create and the amount of features that we want to send to the model. It's a it's kind of hard to define this balance. But if we add new information, theoretically, if you add new information, we can uh, result in a more accurate model. So the process that we of feature creation, we are done more manually. So a data analyst, data scientist will look at the data set and apply some transformations over the data to try to create new features that may add new information. The problem is that we can create features and features and features, and the features can at the end not add any new information to the data, to the problem, or the model, or add new information for us human, but not for the model. So it's a kind of complicated because it's a process that takes time. So one way to do that is automated feature engineering, or AutoFE for short. And what is it? But well, we have a set of features, right? And most of the models of AutoFE use a technique called expansion and reduction, and it's pretty simple how it works, because we have a set of features, right? And we send these features for this expansion phase here. In the expansion phase, we apply transformations of the data. So we apply min, max, log, sum, counts, all types of transformation over the data. And then we will have at the end, as a result, a set of new features, but it is a really large set of new features with all transformations that will apply. And then we are going to apply the reduction phase. The reduction phase, we can think on at the EFS of Aaryan. So what we'll do is just apply a feature selection, and this feature selection will select the best features that was created by here in the expansion phase. But because of this phase here, this method is extremely, it has a high computational cost, because, well, we are going to create a lot of features, and we apply a transformation like sum. over a feature, we can apply another transformation over the feature, but we cannot discard the last feature because the transformation of some that features had may be more informative than this other transformation that we apply over the feature with the sum transformation. So we create a huge set of features, and this cannot turns so well. So as I said, the number of transformations that can be applied to the features is unlimited. So the number of features will grow exponentially, right? And to reduce the number of features, they will apply they the scientists decide to use methods that can learn which best transformation will be applied over the data. So which transformation is best for this feature. It's important, but to just keep in mind that even that they use this learn ability, the expansion and reduction still will occur because we need to learn something. We have to apply this expansion, and then we can learn to at the end apply when we apply the expansion method, we are going to apply more specific expansion method, but still this phase will occur, and still we are going to have a high computational cost, but it's less than using this dummy example here. So these methods that are able to learn are multi-layer perceptron, convolutional neural networks, recurrent neural networks, transformers, or LSTMs. So the MLP, I will just talk about this method really quick because it's part of the work. The MLP does is that we have an input layer. So you have a data set, right? This type of data set. So we are just put this data set on the horizontal, and we are going to pass this data set x1, x2, x3, xn out to this input layer. And this input layer is combined. This, for instance, this x1 here is combined with all the others features on this next hidden layer, and then the same thing on the next hidden layer, and at the end we have this new feature. So it's kind of obviously that when we apply a feature on a MLP, we can create new features because we are going to combine all these features with another features, and then we are going to combine until we have a new feature at the end. And then we can use these hidden layers as the transformations or even the features. For instance, if you cut here these connections, we are going to have 3 new features. If cut here 3 new features also. So the MLP give us these combinations and give us the ability of create new features. But the useful feature interactions are usually sparse. So let's see, we have 4 features, pretty simple, and an MLP that will have 2 hidden layers is basically this MLP. So what we are going to do, we have these 4 features, and we want to see, I don't know, if someone will download a game or not. And then we are going to say, well, which features there are most important for this? Well, yeah, kind of, we can say age, gender. Let's see that. So it's kind of biased, but yeah, age, gender. I think dating, it's also because if a person is dating, it's not playing, but age and gender, it's most important here. So what should happen with dating and name? The combinations that you have, the data and name. So we cannot use these two to create a new feature because these two will not add in any new information, or the information that these 2 features will add is not useful. and then we'll just make the new features make no sense at all. So we should be able to not use these two features, but the MLP will not give us this this opportunity. Will not give us this chance, because to do that we need to learn, and then MLP can learn at the end. Okay, we can train it, but it needs to learn that these two features are not useful. And as the MLP is a huge is massively dense, we cannot learn with precision that these two features are not useful. So in this case, these two features should have the weight equals to 0. And then we are combine the age and gender, and then combine again, and then we have a new feature that is just age and gender combined with some transformations. That would be the best scenario. So to work on that, I propose the FeatGeNN, that the feature generation user evolution and neural networks. So it's pretty simple, kinda. It's based on the architecture developed, but based on the work of Liu et al. And consists of three phases, right? We have the pre-processing phase, that we are going to apply a feature selection method, like the EFS of Aaryan. We apply the EFS to reduce the number of features to the most informative set. So we are going to get the most informative set of features. Then we are going to apply local feature extraction to find the best local interactions. This is done because then we can, here, for instance, we can find that only these two features are the most informative. Then these other two are not informative, then we can discard them. So we are going to apply this local feature extraction to do that. And we are going to use a convolutional neural network to extract these most meaningful features. And then we have the global feature generation that is based the MLP, right? So, but the advantage is that we are going to use a more constrict MLP, a smaller MLP than if you're going to use an MLP directly over the data. So then we use the MLP to extract this global feature, global connections between the features, because as we can see, the MLP has connection to all the data. So all data on the input layer are connected with the other, with each other. So we can use them. So the local feature extraction is just convolution and pooling layers. So the convolution here is on the image, but in our case, it's not using an image. We're going to use a data set, just as a line of the data set. And what what the convolution does is that just apply a filter over the image and then multiply the weights of this filter and then sum the result of this multiplication. Then we sum all this window and we have a new a convolved feature, a new feature. And the most important thing is that when we do this convolution, we are find the most informative features. We are, on the image, for instance, we are going to say which pixel will best represent this window, this convolutional window that we are looking at. So at the feature, on the feature level, we are saying the same thing. Which features are going to represent the most informative connections here? Of course, there we have a huge problem. There is the features don't have a connection with each other. So we can have, for instance, we can have name, car, and school as features. There is no connection whatsoever between these features. So when we apply this convolutional window, we are going to connect features that are not that maybe don't have any connection with each other. So it's a big disadvantage. And when we apply the pooling layer will just look at this window and say, well, which value is bigger here? That's the max pooling. And then we extract that information, and then we do that. We are going to perform a dimensionality reduction that is based on feature selection method, the pooling layer. So the architecture is just we pass these features in the pre-processing phase. The pre-processing phase will select a set of features, and the set of features is the ones that will be combined on this on the CNN. So we pass these select features to the local feature extraction to find the most informative set of features. And then we pass this most informative set of features to the global feature generation to generate new features. And then we just do a concatenation, just do a concat here and just join the two set of features, and we have a new set of features, right? It's pretty simple, at least on the image. Also, we use a evolutional way to learn the weights. In a convolutional network, most of the time we use a gradient descent. But here we are going to use an evolutionary way because we can create a set of population. And then at the end, we use elitism, that is the best set of architectures will pass to the next generation and so on. We can select at the end this this set of elitist features and use them to create the features. So we are going to have different architectures, create different features, selecting at the end like 10 of the population of 100, for instance. So we have a population, there is the all set of architectures. Then we have the chromosome, there will be the configuration of the architecture. We have the genotype, there is the elements contained in the architecture, and then we have the phenotype, there is the values of the genotype. And we have the crossover and mutation, but the crossover mutation can get a little bit complicated when we have different architectures work together. So just keeping simple, we just change the weights of the one convolution or of one architecture with the weights of the another architecture on the crossover. And the mutation, we just change the weights randomly in one architecture. So pretty simple. Can get more complicated than that, but there's no need to this. So the experiment that I have done. So first we have 3 questions that I want to answer. The first was how effective is the proposed FeatGeNN approach? The second is how consistent is the features that the FeatGeNN generate? And the third is how the FeatGeNN will work with the random shuffle. If you shuffle the order of the features, how the FeatGeNN will work, because it's important as the features don't have connection with each other. So if you shuffle, if you use an MLP, for instance, if you shuffle, the performance can decrease or increase. It's kind of lucky, based on luck in this case. So how the local feature extraction improve the method is basically the question. We use this set of data sets with 7 data sets, 4 in classifications, 3 in regression. Okay, and we have within the 7 data sets we use GARG, different architectures on the literature to compare with. The most important here, we are going to look at the base, NFS, and differ. The alpha-2 feature is also is well known because it's a Python library to creation of new features. And in the first question, we can see that we have a big difference first here. In the classification benchmark, we can see that the FeatGeNN has a competitive results with compared with the state of art data sets models. Sorry. It's important that it's two different approach. The state of the art architectures use recurrent neural network or transformer architecture, and the FeatGeNN is use a convolutional architecture. So it's two different approach. The approach using a recurrent architecture is more robust, can give more a better results. Then, but it although but the approach using a convolutional network is a more simple one. So we can see that using a convolutional network, the FeatGeNN, we have results here on the span-based data set benchmark. We have we achieve the best results, and on the other on the classification benchmarks. And on the other ones, we have competitive results compared with differ and the NFS. There's the two best models, the two state-of-the-art models. So we have a really good competitive results with them. But on the regression benchmark, the FeatGeNN don't have a good performance, mainly because it's a more complex type of problem than classification, and the features that are created need to be more precise. So on the regression benchmark, we still improve if you compare with the Bayes or random. The random is we random select transformations to be applied of the data. We have the best, we can be better than them, and the DFS and the auto fits in some cases, but when compared with the differ and the NFS, we don't have a very good performance. But okay, the consistency of the FeatGeNN, the consistency is just I ran the model and then I select the features, the best set of the features of the generation, right? Over 10 epochs. 10 epochs, I run 10 times the model generates, so I get the 10 best features, so it's 100 data, and then we just calculate the mean. So then we achieve these values. We can see that the F1 score of the FeatGeNN don't vary so much. That shows that the model is pretty consistent with the features that generated. And at last but not least, we shuffling the what happened when we shuffling the features. Yeah, so we can see that the result of the FeatGeNN it's pretty consistent, right? So shuffling the features will not imply that we are going to have a worse model or a better model. The model itself is consistent with the results. That's mainly because of the local feature extraction that uses CNN to find the most informative features locally. So as conclusion, we adopt some pre-processing phase. This will decrease the amount of computation that we have that the CNN will have to do. Also, we add a genetic algorithm to create the population and to evolve the architecture and get a better, and we can get a different set of architectures that can create a different set of features in one run. Also, we also create a way to evolve different architectures together. I didn't get into the details here because it's kind of messy, it's kind of complicated to explain, so it's better to keep it simple. And as a final thought, the proposed model are able to effectively generate new features and had competitive performance compared with the state-of-the-art models on the classification tasks. we have to study and try to understand why the model didn't perform so well on the regression tasks, and is something that I'm currently working on. So that's it. Thanks.
Really nice, Samuel. Really nice. I mean, you just yeah, I suppose it's another work that you guys also want to send, right? Yeah, really. I mean, you don't stop. I mean, you just is FPGA, chaotic B. You work with EFS too, and we just have lots of methods to generate features, right? So, does anyone have any questions for Samuel? You guys are pretty shy today. Okay, let me write
I have
down.
one question, like, what,
Jesus Christ.
okay, so the main idea is like, how do you plan the architecture of this whole scenario? The
Oh
main
no, that
architecture.
I don't. For the test, I use one single architecture, the most dumb architecture that I could think of. So that result is not the best one that I can get. Because if I let, the model will create different architectures. I just have to
So,
set the flag. And then the problem is that when we use different architectures, may the uh, the process could become a lot more
chaotic.
slower. Yeah, it's not. Uh, it would not be the best. It would not be the best to create the features, because we will not create the features at the end, because it still will be running. The problem is that when we use different architectures, we have to do the process of how to do the crossover mutation, how this will be performed, because we have different architectures. And this part is it's computationally expensive. I'm trying to find a way to decrease the amount of time that this part takes, but I don't know. It's something that I still am working with. But if I use different architectures, for instance, I use only 10 runs, and I get a better result than I got on the fixed architectures. But the problem is that I cannot say for sure that that result will be consistent, because we have different architecture work together. So I cannot say for sure this architecture will, this different architecture work together will create different features, and this different feature will be good. It's not like I have a fixed architecture. The fixed architecture has these dimensions, it has these parameters, and I know what's happening. That's most important. I know what's happening, so I can say for sure that the result will be consistent. I cannot say for sure when I have this different architecture work together. We have crossover with different weights. We have crossover with different size of kernels, with different size of pooling pooling lay. It's kind of complex. So yeah, I can create the models with different architectures. But right now in this version is I have more confidence with the fixed architecture.
It's like
It's
a global architecture we can use for different problems, something like that.
yeah, like when I define the architecture, it's like I'm doing the ANAS, the neural architecture search. It's basically that. But then
Manual NAS, right?
yeah, but okay, I'm doing the NAS here, and then oh my God, I'm doing the NAS, but uh, when I combine this crazy architectures that is being generated here, sometimes the most of the times important most of the times will not generate a really good architecture, a really good feature, because if you have an architecture that has a I don't know a convolutional layer, a convolutional window with the size 3, and then we have another one with a convolution size 2. well, this one is getting more information than this other one here, and then I'm going to look at the last weight of the last layer of an architecture, and then combine with this layer with the weights of this other architecture here on the first weights. There's not it's kind of messy because the last weights down there on the final of the on architecture don't represent well this first layer, because the first layer is pretty straightforward because we have the same set of features going. So it's just what is changing is how we are manipulating this type of features. So the weights should not be so different because uh, let's say that we have school and car in the same two features here. I don't care. The school and car here don't have a same connection, important connection. So the weight should be zero. So it should be zero for all the architectures. I cannot use if I use the last the last weight down the last weight of an architecture on the initial weight of this architecture will not combine well. So there's kind of some tweaks to be done yet, and as I said, as more details that I get, more confused will be. So it has some it has potential, but uh, it has a lot of work to be done yet. You're free to join me. Yeah, to be honest.
Nice, thanks.
Nice, Samuel. Congrats on your presentation. I think you can go then to Guilherme, our final one for the day. Guilherme?
Here. Okay, so
Good.
let me share my screen. You guys can hear me okay, right?
Yes.
All right.
Good to go.
All right. So hello everyone. Today I'll present a bit about the project that I've been developing here at CloudWalk. It's called Complex Networks and Quantitative Linguistics Applied to the Analysis of the Voynich Manuscript. And should I open my webcam? I forgot.
It is good. Yes.
Okay. What is the Voynich Manuscript? The Voynich is this medieval book found in Europe, and it's written using an unknown script. So it has its own unique alphabet that we don't find anywhere else. And we don't know if it's a ciphertext or if it's a constructed language. So a ciphertext would mean that it was first written in a normal human language and then encrypted somehow. And the constructed language would mean that the language used in the book is an artificial language that was made up by its authors to resemble a real language, but it doesn't really mean anything. So the book would be a sort of hoax. This is the script that is used in the book. So you guys can see that is a very unique set of symbols. And our main goal with this project is answering these two questions here. The first one, is the Voynich compatible with natural language? So as I said, is it a real language that was encrypted, or is it a constructed language? And the second question that we have is, if it is indeed compatible with natural language, then which natural language could it have been written in? So how can we go about answering these questions? Well, we do comparisons. For the first one, we compare the Voynich with random shuffle texts. So we take a bunch of texts and we shuffle around the words randomly. And by doing that, we are hopefully getting rid of any inner structure that the text might have. And so by using these texts, we are representing a constructed language. And for our second question, we do a comparison with texts in multiple languages, And again, we see how the Voynich compares with them. And hopefully we can see if it is closer to a specific language or a family of languages. It could be possible languages that it was originally written in. Now, for the data set that we use in this project, we use the Bible, and that's simply because it is widely available. We can find translations of the books in the Bible in many different languages, basically in any language that we want. And the languages chosen are English, French, Italian, Greek, German, and Dutch. And we add to the data set randomly shuffled versions of the books, as I said, to represent constructed language. So before doing anything, we model every book in the data set as graphs. A graph is a set of connected nodes that interact with each other. We have here an example of a very simple graph. So the nodes are representing entities, and the edges between them just represent a sort of relationship that these entities have with each other. And it's a very useful way of representing systems, and that's because it's very versatile. Most systems can be represented as some sort of graph, and that includes text. So we have here an example of a text that was modeled as a graph. It's the first lines of the poem Bird Norton by T.S. Eliot. And we see here that the words become the nodes, and the edges between them just mean that the words appear next to each other in the text. So if we take, for instance, the first line here, and we take time present, time in the graph is connected to present, and time past, we see here that time is also connected to past. So why do we do this? We do this because many different measurements can be extracted from a graph. And in our case, these measurements can characterize the language of the text. And we compare the values of these measurements to try and answering those two main questions that we have. So when I say that we are comparing the books in the data set, what we are actually doing is comparing the values of these measurements that we extracted from the graphs that were generated based on the different books. So after doing all this, after modeling the texts as graphs, extracting these measurements, we can finally compare them and see how the books are in relation to each other. And for doing that, we use a technique called hierarchical clustering, which is a way of seeing how different elements are in relation to each other. And we use it in all the books in our data set. And these are the results that we got. We see that we ended up with 3 main clusters. I put the results here in a table so you guys can see a little bit better. So again, we ended up with 3 main clusters. Things that are important to notice here. Most of the shuffled versions of the books ended up in the same cluster, and the Voynich is being clustered together in a different group. So that would indicate that it is compatible with natural language, at least based on these results alone. And another important thing to notice is that languages that are considered linguistically similar, they can be found in the same clusters as well. So if we take English and Dutch, for instance, they are together in cluster A, and French and Italian together in cluster B. So that's another interesting result that we got. Now, another thing that we found useful to use in this analysis is linguistic laws and distributions. Linguistic laws are empirical laws that describe statistical patterns found in human language, and we can use them to analyze and characterize our data set, and it may help us in our classification tasks. So the same thing that we did by using the graphs and the measurements that we extracted from them, we can do something similar using these laws and distributions to see how the Voynich behaves, and if it behaves as we would expect a normal human language to behave. So I'll talk about some of the laws and distributions that were used. The first one is called Zipf's law, and it's the most studied linguistic law in quantitative linguistics. And it approximates the relation between the frequency of a word and its rank in the frequency table. So the frequency of a word is simply the number of times that word appears in the text, and the rank of the word is the position in the frequency table. So the most frequent word would be rank number 1, the second most frequent would be number 2, and so on. So here we have the real distribution and the Zipf distribution for the Voynich and for the books in English in our data set. The real distribution is the real frequency distribution we find in the book. It is here the orange curve. And the Zipf distribution is the ideal distribution described by Zipf's law. So in the case of a normal human language, we would expect a big overlap between these two curves. And we see here that, in fact, that does happen in English, but the overlap in the Voynich is much less pronounced. So that's an interesting result that we got. Another law that we considered is the so-called brevity law, or Zipf's law of abbreviation. And it's a very simple law. It just states that the shorter a word is, the more frequent it tends to be. So again, we have the distribution of average frequency per word length for the Voynich manuscript and for the books in English. And we can see that the behavior, the general behavior that the brevity law describes can in fact be observed in both cases. So the shorter words, they appear more, and as the words get longer, the frequency, the average frequency gets lower as well. But if we pay attention to the details, we see that the specific numbers for the frequencies are much lower in the Voynich. So that's another strange pattern that, well, at least when compared to the books in English and also the other books in other languages that we analyzed. Now, the letter frequency distribution, it's very simply the distribution of specific letters in the text. So the frequency for each symbol, it has been shown to be an invariant of language. And because of that, it may be very useful for our language classification tasks. Here we have again the distribution for the Voynich and for the English books. And it's actually very similar, both distributions. And in fact, the letter frequency distribution is the one distribution where the Voynich is most similar to the other books in the data set. So here I put only the plot of the frequency in English, but for all languages, they're very close to what we find in the Voynich. So that's also another interesting result, since in other cases, we see a more divergent behavior, and in this case, it's pretty much what we would expect in the case of a normal human language. So another aspect that the project ended up being about is stop words. Stop words are words with low semantic value. We have here an example. In this image, these words here would be considered stop words. And that's because they don't tell us much about the content of the text. So it's very common to remove stop words as a pre-processing step in many different applications. But it's very hard to do something like this on the Voynich because we don't have a predefined list of stop words that we can simply take a look at and see what the stop words are. So that prompted us to look for a different way of doing something like that, which led us to a measurement called burstness. It's a measure that characterizes the distribution of occurrences of an event through time. So here we have two distributions of an event occurring through time. And we see in the first one, in this periodic distribution, that the interval between occurrences of the event is always the same. So in this case, the burstness value would be very, very low. Now, in the second distribution, in the bursty distribution, we see that the interval between occurrences of the event, it changes a lot. So we can say that the event occurs in bursts. And in this case, we find a burstness value much, much higher. And we can use this because stop words, they tend to be very homogeneous throughout the text. And so they tend to present a much lower value of burstness when compared to more meaningful words. Here I've grouped together the words in the Exodus, the book of the Bible in English, based on their burstness values and their frequencies. And the darker the blue, the higher the concentration of stop words in that group. So we can see here that we have this sweet spot where most of the words in that group are in fact stop words. And it ends up being these groups with very low burstness and very high frequency. So this is just to show you guys how there is indeed a correlation between this measurement and the concentration of stop words. Now, another measurement that we found useful to use here is the so-called TF-IDF, or term frequency inverse document frequency. It's very commonly used to estimate how important a word is. It's given by these formulas here. So it's composed by two terms, actually, the TF and the IDF, which are then multiplied together. And what is important to know in this context is that stop words, they tend to have lower TF-IDF values. So it's another measurement that we can use to try and identify these stop words. Now, for our classification, finally, we are trying to predict if the word is a stop word or not. And each word is then represented by its burstness value and its TF-IDF value. And it's important to note that it's not perfect since word behavior does vary a lot. So we can find a stop word that for some reason in a specific case has a very high TF-IDF value or a very high burstness value. So it's not perfect, but as we will see, it is a interesting first step, and it does give us some important results. Here we have the results of the classification that we tried. We classified the books in English in our data set, so the books of the Bible in English. Actually, two books of the Bible, the Genesis and the Exodus. And here we have the results. So this is the number of stop words that were correctly identified as being stop words. This is the number of stop words that were incorrectly identified as meaningful words. So most of the stop words were correctly predicted. And here we have the number of meaningful words that were identified as stop words. And here, meaningful words that were correctly identified as being so. So we can see that most of stop words and most of the meaningful words were correctly classified. So again, it's not perfect, obviously. We still have here some false results. But but it's already very interesting considering the limitations that we have in this case. So for the conclusions, we conclude that complex networks and statistical analysis are versatile tools that can be used well in our case. There is a lot of design choices yet to be explored, certainly, and we can use sparseness and TF-IDF values to help predict the stop words. Now for future work, we've got to expand the data set, so include more languages and more books to represent each language. We need to refine our list of measurements that we are using for our classification tasks, for the analysis in general. We've got to incorporate new techniques into the framework. So there's a lot that we can, a lot of different related techniques and frameworks that can be incorporated here. And we can consider more features based on linguistic laws and statistical distributions for the classification tasks. So it's, again, there is a lot that has been done in this field, and there is a lot that can be added to this specific framework. So that's it for me, guys. Thank you very much.
Really, really nice, Guilherme. Congrats.
Thank you.
So, does anyone have any questions for Guilherme?
I have one question.
Oh, please.
Okay, so I saw the results for the stop words for English language, right? But I didn't saw the results for the Voynich Manuscript. So did you run it then? How many stop words did you?
We can't know for sure if the words in the Voynich are stop words or not, because as I said, we don't have a list of predefined stop words. So what we do in that case in English, we use our model to predict, and we see if that word that we predicted is in a list of predefined terms for the English language. And by doing that, we know if the word can be considered a stop word or not. But for the Voynich, we can't do something like that, right? So we can only kind of guess for the behavior that the word has within the book.
Yeah, you don't have the true labels, but I think it's still interesting to know how many stop words would be predicted, you know, and what proportion of it against the vocabulary.
Yeah, I see what you're saying. Yeah, I did do that, but I didn't include in the presentation. I don't remember exactly the percentage, but it was more or less the same that we get by trying the model in different languages.
Yeah, but that's really interesting, because then, like, you could say for a given transliteration, we have like some list and show like some of the words that potentially could be stop words in this language in Voynich. Yeah, that's really an interesting idea. Yeah.
Yeah, and also to compare with this proportion for random text, maybe.
Yeah, that's interesting.
Yeah, random text.
Yeah. Said,
yeah, because random text, the burstness would be very different, right?
Yeah. Nice, thank you, and congratulations for the work.
Well, thank you.
Yeah, really nice, Guilherme. So, no more questions for Guilherme. So, well, so I think we can end then the symposium. I think thanks for everyone that presented, and thanks for everyone that participated. Pedro, any final comments or?
Yes.
So
I would like to say congratulations to all the interns. You have done amazing work throughout the year. Definitely cool to see the evolution of your research. Some of them, we found a lot of intersections with CloudWalk. I hope to explore them
I think that should be like one of the ideas. Like if you guys felt something like, oh, maybe a pain point and something like that, maybe we could start talking, right? We can't promise anything because we kind of do a lot of stuff already, but I think it would be really nice to know, and maybe in potential future projects. I think that would be really awesome.
of course. Yeah, and we will make this video available for everyone. So it will be public. Yeah, so if you want to watch it again, or you want to read the papers or have access to the presentations, just reach us out.
Yes, and maybe it's also going to be public on YouTube, right? So
Yeah, definitely will be public on YouTube. Let's do this pretty soon, possibly this week. And I shared the link with all of you.
yes, and just for let everyone know as well, you know, the first symposium that we held in the end of the last year also is on YouTube and CloudWalk's YouTube channel. So if you want to show to someone else, you know, that may find this interesting, you can find it on YouTube, so you can send a link there too.
Awesome. All right, I think this is it. Thank you everyone for participating. Awesome to have you.
Thanks, guys.
Bye-bye.
Bye-bye.
Okay, I think
Thanks, guys. Good work.
to stop recording before finishing.
Let me stop recording.